All right, folks. My phone wasn't loud enough. There he goes. Okay, picking up where we left off in this chapter 5 on simple mixtures. Okay. So where I left off last time was discussing this idea of an ideal solution. And one of the criteria for an ideal solution is that the enthalpy of mixing is 0. So when we mix two things together, no heat is evolved or absorbed. That's one telltale sign of an ideal solution. There's a couple of more, mostly related to the vapor pressure, and you can see that's what I've got going on this graph. So let's talk about this for a bit. So we note that when I have a mixture of liquids A and B in some closed container, it will be in equilibrium with A and B vapor, with the vapor of A and B. Okay, so we can say, suppose the chemical potential of A, and I'll put a star on there, and that denotes, the star tells me it's a pure phase, so that's going to be my nomenclature. And for the gas, okay, and we note that that's going to equal the chemical potential of the pure liquid. So these two phases are in equilibrium with each other. Okay. Similarly, we can say that about B as well. Okay. And B gas is in equilibrium with its liquid as well. Okay. So now if I go and expand on this and write this equation for the chemical potential of the liquid, so that's the pure chemical potential of the liquid, I'm going to get this standard value, so the reference value, excuse me. And this is this equation, that goes the reference value, or the value that's the initial value on the integrand, plus RT natural log, and this works out to be PA star divided by P0, where this PA star is the vapor pressure of pure A. And this P0 is just standard pressure, which is actually 1 bar, okay? So now if we were to expand on this and write the chemical potential of the solution, and specifically now we're talking about the chemical potential of A in this new solution. Okay, well, this equation is going to be modified just a little bit, and it's going to look like the following. It's going to become mu A, I'm going to put a standard, and I'm going to put the star right there because the star tells me this is the pure A. So the chemical potential of A in the solution equals the chemical potential of pure A plus RT natural log of the vapor pressure of the solution relative to the vapor pressure of the pure liquid. Okay? And so if we were to continue expanding on this with B as well, and we also use Dalton's law of partial pressures. I'm not gonna fully derive this, but we would end up arriving at Raoult's law, okay, that says the vapor pressure of the solution is equal to the mole fraction of A times the vapor pressure of pure A plus the mole fraction of B times the vapor pressure of pure B, okay? And then, which means I could expand this equation, or I could write it slightly different for the chemical potential of A in the solution. Okay, it's going to equal the chemical potential standard of pure A, so as if it's by itself, now plus RT natural log of the mole fraction. Okay, so this ratio of P, of the vapor pressure of the solution relative to the vapor pressure of pure A, that's just going to give us the mole fraction, okay? And so this equation is for ideal solutions only. And so this is kind of a major criterion for ideal solutions. So this linear additive way of adding up the vapor pressures, which we know as, let's see here. I can never spell this. Raoult's law. R-A-O-U-L-T. Raoult's law. Okay? So here's a graph of Raoult's law, right? And if we look at this, a mole fraction of A from 0 to 1, and of course I could also make another axis up top here and write that as chi B. And when the mole fraction of A is 1, the mole fraction of B is 0, and the mole fraction of A is 0, the mole fraction of B is 1, right? So now if we look at what we've got going on here, so on this graph, okay, here's my PA star. So that's the vapor pressure of just pure A. And as you can see, when the mole fraction of A is 1 and the mole fraction of B is 0, the total pressure of the solution is just the vapor pressure of A. Similarly, when the mole fraction of B is 1, then the vapor pressure of the solution is just equal to the vapor pressure of B because there is no A. Okay? But now what we see on these graphs are actually the equation here is, so for A, I'll try to write this along it, so that goes chi A times PA star. And then along this line, this is chi B times B star, okay? And so when I add those two together, as is in Raoult's law, I arrive at this total pressure line, okay? And so if a solution obeys this law, in other words, I can just add up the mole fraction weighted vapor pressures, then it's an ideal solution. In addition to this criterion as well, okay? So let's move forward with that, and let's talk about now ideal solutions, and instead of saying real solutions, we call them ideal-dilute solutions, okay? So let's look at a real example of an ideal solution here, benzene and methylbenzene, which, could be like toluene, right? And then methylbenzene. Man, I haven't drawn an organic structure like all year. Okay, bam, there we go. So as we can see, benzene and methylbenzene are both really similar. So it's actually not surprising at all that these two make an ideal solution. The golden rule of chemistry, right? Like, likes, like. The golden rule of chemistry. Like, likes, like. So methylbenzene and benzene like each other because they're both very similar. And so now if we were to look at this curve, here the vapor pressures of methylbenzene, and so you can see this would be the vapor pressure of pure methylbenzene right there. And then here on this other side, this would be the pure vapor pressure of just benzene. And then now we add up both of these lines, and that gives us the vapor pressure of their solution. Okay, so what about a real solution or an ideal dilute solution? So for example, carbon disulfide and acetone. So the dotted lines here are the Raoult's law line, R-A-O-U-L-T-S. So these dotted lines are both Raoult's law. And you can see there's actually a region here for acetone where it's following along this Raoult's law line, but then it deviates from that. And you can also see for carbon disulfide, just for a very small addition, so in other words, for a very dilute addition, it's also following the Raoult's law line, okay? So let's